I tell you ahead of time, these lectures are very technical. They involve a lot of equations and modeling and so forth. And then we'll close out our time together talking about the geology of sequestration, and in particular, what are the hazards associated with sequestering carbon dioxide underground. And then we'll close with some comments about geoengineering, which are some proposals that many of our community have come up with to suggest how we might mitigate or deal with carbon dioxide in the atmosphere. So that's a little bit about our time together. I will say one or two things about the nature of the course. I will try to practice with you a couple of things that we do in Berkeley in the classroom. So while most of this is colloquium-style presentation with slides, there will be times when you have to work with the person sitting next to you. So just be prepared for that. I promise I will not shame any of you in front of the others, but you will have to do some work together in the course of our time together. So the first part of our discussion is an introduction to energy and climate, which sets the stage for why carbon dioxide in the atmosphere is such a significant problem. So let's talk about the news. Of course, many of you have heard about the agreement in Paris that happened recently this last year. A great deal of activity and excitement over an agreement reached by many of the nations of the world to limit the amount of carbon dioxide into the atmosphere. It's been hailed as a really great agreement, and even the United States, at least at the moment, agreed to it. So 195 countries to limit the greenhouse gas emissions. The idea is to limit global temperature rise to less than 2 degrees centigrade, and the idea was to aim for 1.5 degrees centigrade. One thing that will happen as a context of this course is you'll realize that's impossible. We've already lost that goal, unless something very drastic were to happen, which is unlikely. Nevertheless, that was the ambitious goal set out, and then net zero emissions by the nations of the world by the middle part of this century. So by the time you and your children are in their teens, then this would be achieved. And then, of course, a framework for how to deal with nations that don't comply and say they do, and for review, constant review and updating. And perhaps most important is the notion that rich countries, which by and large have been responsible for most of the CO2 emissions into the atmosphere, would help the poorer countries by providing finances in particular to both adapt from climate change and to convert to, for example, renewable energies. So as we pose these problems this afternoon, the questions we have to keep in mind is, what does this mean, 2 degrees C? Where did that target come from, and why did people choose that? What about the equity issues associated with economics and science? Because, of course, we live in a complex world where posturing with regard to the environment is also a critical part of how decisions are made. How do we enforce and monitor what happens, and what if we can't measure the results? Or, in the case of the United States, and I'm not happy to say this, but it may well be that measuring the results of climate change are not allowed. And what do we mean by clean energy? What does it in fact mean? And the picture is somewhat informative there. And of course, the whole point of this course is, where does carbon capture and sequestration fit in with respect to all these questions? So here's the big picture, the sort of giant overview of what's happening. We imagine a power plant producing carbon dioxide. Oh, sorry, I got to stay on camera. Carbon dioxide stays from the power plant. We imagine a unit in which carbon dioxide is separated from the other gases. We'll learn more about that later. It's compressed, transported, and then injected underground. And that's the goal we have in mind. So who's the main character in the drama that's going to play out for the next 10 hours or so? And the main character is the carbon dioxide molecule, shown here with a variety of pictures from the internet. Now, it's an uncharged molecule. It also has a quadrupole moment, as indicated by the charges in this particular picture. Carbon dioxide fits in this very funny place in terms of the energetic states associated with carbon. So I assume my audience is familiar with basics of high school chemistry. And so carbon in its highest energy state exists as, for example, coal or pure carbon. And the lowest energy state would be a mineral carbonate, often associated with the White Cliffs of Dover in England. And of course, carbon dioxide sits there right in the middle and you recognize that there are very large energy barriers going from carbon dioxide to carbon and vice versa. And we recognize that chemistry tells us that the rates by which we go from this place to this place and back depends on temperature as well as many other parameters. So what about carbon dioxide? What do we know about it? And it's a relatively straightforward molecule. Here's a pressure temperature diagram, a phase diagram of carbon dioxide. And you'll recognize here we are, room temperature is around here. And we recognize that at high temperatures and high pressures, carbon dioxide exists in several solid and fluid phases, but that there's a critical point for carbon dioxide that's relatively low pressure and relatively modest temperature. And the reason that's important is because the best and most facile way to transport carbon dioxide is to put it in a pipeline and move it as a supercritical fluid. Its viscosity is low, its density is high, and it's relatively easy to manage. And so the fact that CO2 is accessible as a supercritical fluid turns out to be very important. We'll also discover in the geology of carbon dioxide that as we inject it underground, after about a kilometer or so, the pressure and temperature of the Earth is such that carbon dioxide would exist as a supercritical fluid anyway. So this phase diagram tells us a lot about where we're going to be going with regard to managing carbon. So here's the story that we have in mind. The carbon dioxide molecule will be injected underground. Because as a supercritical fluid, it's actually less dense than the brine or other rocks around it. Carbon dioxide will rise, and that's, of course, a potential hazard. If we're going to put something underground, we'd like it to stay underground and not come back to the surface, and we'll come back and talk about that in a few hours. But the idea is that the carbon dioxide molecule then will transport, but along the way, before it gets anywhere near the surface, it becomes trapped. And we'll find that there are 4 trapping mechanisms for carbon dioxide, and that there are many, many places throughout the world in which there are geological formations in which carbon dioxide is and can be stored stably. So understanding the geology and physics of this process turns out to be, of course, relatively important. As I pointed out before, the density of carbon dioxide varies a lot with pressure, so this is a cartoon which just reminds us that if this balloon represents CO2 at the ground, then if we put it underground, let's say on the surface, if we put it underground at 2.5 kilometers, we recognize the density is quite small, and really at just about a kilometer is when we approach the supercritical fluid phase. So as I said before, dealing with carbon dioxide underground is dealing with carbon dioxide as a supercritical fluid. So the notion that we were going to take carbon dioxide and put it underground is actually an old concept. These are old technologies that date even me. And this is because for many, many years, we have used carbon dioxide to enhance the production of oil. This is particularly popular in the United States, where carbon dioxide is injected as a supercritical fluid in rocks in which there's a modest amount of oil that's trapped. The supercritical fluid pushes the oil to a recovery well, and then the CO2 is recycled and sent back down again. Many, many thousands of tons of CO2 are used in this process to enhance the recovery of oil. So these kinds of chemical processes are already known and have been used for some time by the oil and gas industry. Here, for example, is a map of the United States, and shown on the map are existing pipelines for supercritical CO2 transport that have been built specifically to extract oil from underground. So the notion of putting CO2 in a pipe is not unusual, and the notion of pumping it underground is not unusual. There's a large existing infrastructure to make that happen. The idea that you could take natural CO2 out of a gas mixture and purify it is also an old technology. It's sometimes called natural gas sweetening. But if you follow this process diagram for a minute, look and see what happens out. Here you have a wellhead that goes to a well underground, and that's producing natural gas, maybe other kinds of fluids, but certainly natural gas. And they come up into this device, oil and water are separated. And then what happens is, in this column, of this particular device right here, CO2 enters that is mixed with things like hydrogen sulfide. And as a result of this process, CO2 comes out, and hydrogen sulfide comes out separately. And then CO2 is then stored or used for enhanced oil recovery. and the hydrogen sulfide is often used to further make products such as gypsum. So the notion of purifying a gas stream to separate CO2 from other gases is well known. It's been used in the hydrocarbon industry for many, many decades. And the rest of this diagram just goes to show what happens to the rest of the gases, and ultimately you produce natural gas or methane, which is sent into the pipeline. So, climate change has upended all these notions. And the reason it's upended all these notions is that science, the technology, economic policy, and politics are all completely overwhelmed by the scale at which we produce carbon dioxide. So while it's one thing to talk about enhanced oil recovery and natural gas sweetening, if you think about the scale of CO2 required to manage, it overwhelms all these fields, which is one of the reasons why it's such an enormous technical challenge, especially a challenge for China, India, and the United States. We'll come back to in a few minutes. Let's take a look at the world energy consumption, because really it's all about energy, because as we use energy, we produce carbon dioxide. So here is a unit megatons of oil equivalent. We'll come back and talk about that, what that means in a minute. Here's the year up to 2012, and you can see the breakdown here that oil represents a significant part of it, and coal, a very large part of it. And then we see the emergence in recent years, just at the very top here, of renewables. And there are some countries, and we can thank Professor Blumich for Germany's leadership in the role of renewables, and other countries as well are making a very large difference here. And hydroelectricity is something some people have and others don't. It's also very difficult to manage. But if you look at this graph, you recognize that a significant fraction of the world's energy consumption is related to oil, natural gas, and, of course, coal. So today we are at 13,000 megatons of oil equivalent is our energy consumption use. And so now we have to kind of get our mind around it. If you're a chemistry student or a physics student, the numbers associated with this are absolutely staggering. So a TOE is a ton of equivalent oil, which is the energy released if you burn a ton of standard oil. That turns out to be 42 billion joules. So the world energy consumption is 13,000 times that. That's a lot of kilograms of equivalent oil. And if you ask, well, how big is that per year? And if I take the density of oil, as I might find in a textbook, I discover that we have 2.5 cubic kilometers of oil equivalent per year are being used just so that we can generate the energy we use every day in our lives. That's a rather enormous amount of oil equivalent. Another way to look at it is what are these 13 million ton equivalents and 14 billion joules work out to in other units. These are popular units for engineering and other disciplines, that many kilowatt hours, that many BTUs. And it turns out in the energy field there's a unit called quads, the quadrillion BTUs, and so this is the number that you often see when you read the popular media and you read the newspaper about energy equivalent. They often use the units of quads. And you can see that that's a lot of energy. So let's take a look at the scale. Here's a log scale for energy in joules, and here's some of the things I'm familiar with. So a bicycle ride from Berkeley to San Francisco, our typical lithium-ion battery, and you can see the energy associated with these on a log scale. And we notice that the output of the sun per second is up here. So that's sort of one extremum, as it were, right, of energy. But if we look at, for example, things we've read about, here's the Japanese earthquake and tsunami that happened a few years ago, devastating effects associated with that. And here's our per capita energy use, right here, and so forth and so on. If you look at the scale, recognizing that it's a log scale, you see the staggering numbers associated with our energy production, and indeed with just the things we do routinely, such as boil water to make a cup of tea. So here's the annual world energy use right there. So we are burning the equivalent of this many tons of oil per year, and we can take stoichiometry. This is the chemical formula for a typical oil. Here's how much oxygen would be consumed, the amount of carbon dioxide produced. And if we turn out, that turns out to be a lot of carbon dioxide. And we're going to come back and revisit what those units are and various things along the way. So that's the mass of carbon dioxide, and that also is the mass of carbon. So as you read the literature about carbon dioxide in the air, what you find is that there are graphs that contain the mass of carbon dioxide in the air or the mass of carbon. The units are often mixed up, so as a student you need to pay careful attention. The mass of carbon in the atmosphere would also include methane. And we'll come back and talk about the role of methane in climate change shortly, whereas mass of carbon dioxide, of course, is just that. And there's the stoichiometry of the fuel. So here's a million metric tons of carbon released from the burning of our fuels, according to the various kinds of industries, as a function of year. And here we are in 2010. And of course, you can see the total is really quite alarming. So almost 8,000 gigatons, as it were, of carbon per year are being introduced into the atmosphere. So I don't know how to convince you, maybe when you're with your friends tonight over tea and talking, what does it mean 8 gigatons of carbon per year into the atmosphere? Even though the atmosphere is a very big place, it's a staggering amount of carbon. And there you see that, for example, things that students often don't realize is that cement manufacturing is a huge energy consumer and a non-trivial contributor to carbon dioxide into the world's atmosphere. And so you find that chemists and chemical engineers in many parts of the world are looking at technologies for reducing the CO2 emissions from cement manufacturing. So here's a nice picture of our coal-fired power plant. And so the question you might ask is, well, if that's CO2 coming out of the smokestack, how much of that can we actually capture? Because there are many producers of carbon dioxide. For example, your vehicle. Are you going to be able to capture carbon dioxide from the exhaust of your vehicle? So let's take a look, and I have these numbers for the United States. Might be interesting in all your spare time, students, to think about where you would find these numbers for India and have them at your fingertips. So here's electrical power is 28% of the U.S. energy related sector. Transportation, another 25%, and then you see these here. And now, if you look at the energy related source, according to the fuel, you realize petroleum, coal, and natural gas more or less split equally, although petroleum is a little more. But the coal sector, which provides electrical power, is certainly the easiest place to imagine doing carbon capture and sequestration. The coal-fired power plant is fixed, and it represents a very large producer of energy. These diagrams are produced by the Lawrence Livermore National Laboratory in the United States and published every year. And what they do is they represent the flow of energy in our systems and what they are used for. So, for example, here's petroleum, and the units are not so important right now, but you can see this is 35, a rather large fraction. And you see that almost all of that is used for transportation and a little bit of industrial. So these flow diagrams help us understand a great deal as to where the carbon dioxide is coming from and where it's going to. And here you see coal right here at 19.7, and this bar goes right to electricity generation. So coal is a natural place to think about working with carbon capture and sequestration because it represents a fixed in place source of coal, and it can be represents a significant part. So the other issue, of course, is how efficiently do we convert energy to electricity. That's another sort of irritating matter because the efficiency is typically on the order of a third. That's the Carnot efficiency, largely associated with boiling water and blowing turbines. And so we use a great deal of coal, and yet we don't produce much electricity from it, and therefore a lot of CO2 is produced. So what percentage of our electricity generation comes from coal? In the U.S., it's about 45%. In Germany, it was higher, and now it's, I think, only a third and falling rapidly. And I actually don't know the numbers for India, but I'm sure they would be interesting to find out. So here we have sort of CO2 emissions from sources. These are European numbers now. Those that are addressable by carbon capture and sequestration, that is, they come from a fixed source, like a cement plant or coal-fired power plant, stationary sources. The transportation sources are untenable to capture right now, although I've been to a conference recently in which some of our colleagues from Europe, they claim they figured out a way to capture CO2 from the tailpipe of a car in a sustainable way. I don't know the details. I'm curious to see how that can work. So if we take coal, so if you take stationary sources, about half of them are from coal, and then here you see the cement industries and so forth. So it's clear that carbon capture and sequestration from stationary sources and coal also makes sense in Europe. So we should start with the existing power plants, okay? Because those are in place already. So now I would like, this is one of your first exercises, you need to introduce yourself to the person next to you. And just take a minute or two, would you please, and ask these questions with your colleagues. And then we'll come back in 1 minute. Please. Okay, let's come back together for a second. I'll come back and visit these questions. I'm just wondering, would anybody care to tell me anything about these numbers? Does anybody know? A list where you would go to find out? Yeah.
So, like, if you ask me the energy percentage from the fourth number plant, it's around 40%.
So it's about the same as the U.S.
Well, maybe a little bit more than that. We have government thermal power plants. Two are in Bathinda, one is in Rohtak, City District, 3 plants. And recently, in the last 5 years, we put 3 more thermal power plants. One in Amritsar District, one in Rajpura and Kerala. So we have now, I think, 5 thermal power plants in Punjab. It's a very small state, it's a very small area compared to India. And if you ask about that hydroelectric power plants, we have one on the border of Punjab, one is in After Dam and other two. So I think we are also going for solar plants. And recently there is one power plant, it's a solar-based rooftop, that's world largest one is opened up in Yash. Just 6 months back, around 6 megawatts. And two other plants with 5 megawatts. But it's a small as compared to, if you compare this one. Because they are about, some are 800 megawatts, 600, 1200 megawatts. So this is something. But still now we are moving more towards the non-conventional resources. And here maybe we don't have very good data sources for these things.
Well, somebody knows a lot here, so thank you very much. Okay. Good. So if we go back and look at stoichiometry and the combustion process, and we ask ourselves, what is the form of carbon that we're likely to see? So here's a table which I took from the internet, which lists the various kinds of carbon. There's so-called heating value, and of course the heating value tells us how much heat you get per pound or per kilogram of this material, and that's directly related to its heating value and its source as electrical power generation. So for example, anthracite, which is this sort of very dark-looking black coal, has a relatively modest heat of combustion. So we have the stoichiometry of the fuel, and then we have the emissions per BTU. And so we can figure out then the various types of coal. And I just wanted to call attention to the fact that, for example, lignite has 200 pounds of CO2 per million BTUs of energy. It's an interesting number to know. The other interesting number to keep in the back of your head is that natural gas is not quite half the CO2 emissions that coal, for example. And so this is one of the reasons why the United States has recently looked like such a favorable player in the carbon emissions world, and that's because of, for economic reasons, not policy, for economic reasons, the United States is moving many of its fixed power generation to natural gas, and as a result, the CO2 emissions are falling. But it's not because of a policy, it's because of the tremendously cheap prices associated with natural gas which derive from various processes to produce it, which we'll come back to when we talk about geology later. So, different fuels have different energy contents, and so what that means is that if I look at the amount of CO2 produced for the amount of energy produced, I have these various characters, and you'll recognize that coal, again, is the highest value. So coal produces almost twice as much CO2 as natural gas per unit of energy. So let's take a particular coal-fired power plant in the USA. This is one in the southeast part of the USA, near the state of Georgia. This particular coal-fired power plant burns 1,288 tons of coal every hour. It's a staggering amount, and one way to think about that is that either 2 to 5 trains per day full of coal arrive at this power plant, and each train has 124 cars that are filled up with coal. It's just a staggering amount of material that's being consumed each day for this particular power plant, and I think this is a 500 megawatt unit. So how much CO2 comes from one particular power plant? It's a figure that's nice to have around. Let's take a medium-sized 500 megawatt coal-fired power plant. That's sort of the generic one that you might find. And then you have to do some unit conversions to look at how much energy you get out of coal, the efficiency of the power plant, the stoichiometry of the combustion, and that turns out to be 70 cubic meters per second of carbon dioxide. So it's an interesting number to have at your fingertips. I'm going to guess that this room, it would be an interesting exercise for you to figure out how many cubic meters this room is. But I'm going to guess it's on the order of 100. So you could imagine filling this room with carbon dioxide every second, 24 hours a day, 7 days a week, 365 days a year. That turns out to be 4 megatons of CO2 per year from that particular power plant. And of course, you can scale according to the size of the power plant, so you can just take this number and multiply it by 6 to figure out a 3 gigawatt coal-fired power plant. The largest, I think, in the USA is a 3 gigawatt one, although I think there's a 6 gigawatt one coming online relatively soon. So it's a staggering amount of CO2 per power plant. So another way to think about it, which makes sense to students in the USA, is that if you take the Empire State Building and imagine it as a hollow rectangle, then it would fill with CO2 every 4 hours just from one particular coal-fired power plant. And so that's the scale that we're talking about. And you might ask, well, how much is that per year, or in for that matter, the lifetime of a plant? Because the lifetime of a coal-fired power plant is 30 to 50 years. So that's an interesting number. We're going to come back and look at a diagram for that a little later on. But another question that often comes up is, well, are we going to run out of fossil fuels? Are we just going to be working with renewables any day now? That any day now has been moved further and further away in time as both our energy efficiency increases and our ability to extract resources from underground improves. But here's a typical diagram. We call it the carbon age now. Here's this particular is the carbon stocks in the ground and in the atmosphere, and we see that an enormous amount of CO2 is projected.
2100, so how much of these fossil are in the ground? So here's the other half of that diagram, and we realize that gas, oil, particularly coal, there are enormous stocks of coal underground, and it's unlikely that we will ever run out, really, to be honest. We can't, projecting more than 100 years in the future looks like science fiction. So, but we have a tremendous amount of resources underground. So the answer is, when will we run out? Well, we'll run out of patience first. But these known reserves represent, if they were all burned, 4 times the emissions of CO2 into the atmosphere to date, and the consequences of that are amazing. I found this interesting quote by a Saudi Arabian leader in the oil industry. During the 1970s, there was a famous embargo in which the prices of oil skyrocketed. And he made this quote that I find very interesting, that the Stone Age did not end because of the lack of stones, and the oil age will end long before the world runs out of oil. And I think that's a very interesting prediction. Let's take a look at another view of it. Here's the fossil reserves in terms of the gigatons of carbon. Here's what's in the atmosphere right now, and this would represent about a 2 degree C temperature increase. So you can imagine the consequences of removing these and bringing them up into the atmosphere. Another way to look at it is if you're an economist, if you're a capitalist, and you're thinking of extracting resources from the earth and making wealth, that represents $27 trillion of wealth underground. So if you want to stop taking that wealth out, then you have an enormous challenge for you politically, economically, and socially. Because there are many, many forces that feel that extracting these resources and generating this wealth is a good thing. Okay? And you may be one of them. So it's an interesting attribute to think about. So the notion of leaving it in the ground becomes a bit problematic for many. Not all, but for many. And of course, carbon capture and sequestration represents a way out of this particular trap because it does allow for the extraction of these resources to produce energy, provided the carbon is returned, then at least some of the environmental impact is mitigated. So one of the motivations for carbon capture and sequestration is that it allows the wealth that exists underground to continue to contribute to our economy until we have a rational scheme for replacing it with renewables. I have to tell you, however, that I've gone to meetings, I've gone to schools where I made this kind of presentation, and there were protesters in the back of the room yelling and shouting at me that I was serving big oil, and I really was just getting rich off of what Exxon was digging out of the ground. And so it's a criticism I'm aware of, yeah? But it's an interesting fact to think about leaving this kind of wealth behind. Let's talk about the existing coal-fired power plants. Suppose we weren't building any new ones. As I mentioned before, the typical coal-fired power plant lasts on the order of 35 years or something like that. And here's a fraction of the coal-fired power plants that are surviving as a function of time. We just stop building and let the old ones die out. And so we see that we have another 30, 35 years of coal being burned in order to meet this needs. Another way to think about it, and I'm not sure how coal-fired power plants are financed in India. I suspect probably through the state or the government. In the United States and many other countries, a coal-fired power plant is in fact financed with the help of a bank. You get a loan for $10 billion, you build a coal-fired power plant, and then the rate generators, that is the people who use the power from the coal-fired power plant, are paying against that loan for 30 years. And so if we were to shut that coal-fired power plant off today, there's a bill of anywhere from 1 to 10, small to many billions of dollars that's left to be paid for the construction of that coal-fired power plant. So who pays for that? In the United States, this is a vexing economic and political problem. It's one of the reasons why people want to leave the coal-fired power plants running, so that they generate the revenue to pay back the loans that we used to create the plant in the first place. Very vexing. So, but you see, we're going to be 70 years out before they're all retired in the United States. As I said, they last about 30 years. Another way to look at that is so-called commitment accounting. And I want to ignore the lower half of this scale for a minute. I just want you to take a look at the emissions of gigatons in carbon that are committed based upon the coal-fired power plants that are built and in place today. And you see those commitments are still increasing. And here they are breakdown by coal, natural gas, and oil. And you see the various breakdowns there. So economists, social scientists, and policy analysts look at coal-fired power plants from the point of view of the various commitments. And they also recognize that CO2 emissions from coal-fired power plants are likely to continue. Let's ask who are the players associated with CO2 emissions. This particular graph, its paper's a little out of date now, but you get the idea. The main players are still the same: the United States, China, the UK, India, and Saudi Arabia should be in here somewhere, maybe not so visible, represent the largest in terms of gigatons per year of emissions. And that may change in both India and China as they build more and more coal-fired power plants. So let's see, here's the total remaining commitments broken down by the rest of the world, and you see these commitments are still rising with time. And this is the commitments in gigatons of CO2 by the various energy types: oil, gas, coal. Coal is still rising. I went to a conference in Germany when I was visiting my colleague Professor Blumenthal last year, And I went to a talk by a German economist who talked about this current era as the second generation or the second revolution in the use of coal, and how coal is transforming the world in many ways. But he called it a renaissance in coal combustion. So worldwide, we have roughly 90 gigawatts per year of new coal capacity coming on, versus a third of that number in the decade prior to the change of the century. Our committed emissions are growing at 4% a year. Retiring these means retiring our whole infrastructure that is being built. And so this is yet another reason why I submit that carbon capture and sequestration is an essential part of our energy policy plans worldwide going forward into the future. So this is a good time for me to look at another graph. And I have to confess that I'm not completely sure this will work, but let's give it a try. If you want to have fun with your friends one Saturday evening, what you want to do is go to gapminder.org. It's this absolutely amazing website in which you're able to use databases that have been created by the owners of this website to create graphs that tell us about the impact humans have on the world. I've downloaded a graph, and hopefully it'll work for you in a minute. This is the CO2 emissions per person. On this axis, it's a log scale. This is the income per person, the GDP per capita, income adjusted. Okay, so CO2 per person, income per person. You would expect them to be related. I hope you would. The size of the bubbles that you see will represent the size of the populations. And then we're going to march in time from 1800 to the present day. Now, I've highlighted United States, China, India, and Germany to be the bigger bubbles, but all the nations will be shown. And if I got this correct, then it should work. If I don't have it correct, then we will find something else to do. So this is the year, and you can see what's happening to the world economies. Here's China, here. You'll notice the effect of World War I and World War II, quite dramatic. But you see the trend. India and China marching forward. U.S. leading the way. This is CO2 emissions per person versus the GDP. So, what does it tell you? Wealthy nations emit more CO2. And as wealth grows, so do the emissions. These kind of graphs are very, very powerful teaching tools, and they're a lot of fun to play with. So I encourage you in all your spare time to go take a look at that website and enjoy it. Okay, here's another projection according to the countries that have wealth and those that don't, and you see that the projections are that the wealthy countries will mitigate a large amount of their energy consumption as time goes on, and the so-called developing countries will not. In California, I'm particularly proud to say that the emissions per person has been constant in the state of California for the past 20 years. Whereas the energy used per person has been going up. And there's a lot of reasons for that. For example, now when you go to buy a washing machine or other appliance in your home, the label on it is the price, and then next to it is the amount of CO2 emitted per day, week, month, or year by that device. And shoppers now actually pay attention to this, and they actually buy the device that may be more expensive that in the long run actually uses less electricity or less CO2 produced. So those kind of market force tools have been shown to be effective, and they certainly are effective in the wealthy countries. Well, what about the effects of climate change? If the wealthy countries are producing them, are they the ones suffering the most? And the answer, of course, and I see you know this already, is that if you look at the CO2 emissions per capita, the big emitters, and then look at those who are most likely to be impacted by climate change, there are parts of the world that are not associated with the most CO2 emissions. And so here we are faced with this vexing public policy problem, this issue of how do the wealthy nations think of themselves when talking to other nations about carbon emissions. So recently a team of economists came up with a scheme, a plan. I think it's quite interesting for us to take a look at this. So this is the annual emissions per person in the year 2030, projected according to usual economic projections. And here on this axis is the number of people who contribute to those emissions. So here you have this little square here. This is 1.1 billion people who emit more than 10.8 tons per year of CO2. And over here on this axis is a much larger number of people with very low emissions. And so the proposal by social scientists and economists is that we look at not at nations but at people in terms of their CO2 emissions. And so if we want to reduce the global CO2 emissions by 30%, we need to cap all these other emitters at 10.8. And then if we lower it just a little bit more, we give an allowance to many, many people who are much poorer to have a little more CO2 for their growing energy infrastructure. So it's the notion of using individuals and not countries that subverts this notion that nations need to pay for other nations. That's a very interesting and exciting scheme. It was discussed a great deal at the Paris conference as a scheme for dealing with this situation. So how do we make the slope go down? Carbon emissions, billions of tons per year, is a function of year. Here we have been, and of course we would like to see this, and the question is how do we make it so? And what are the limiting cases, and what can we control? And what can carbon capture and sequestration do to control this? So I'm noticing my time here says that we've been going 43 minutes and 40 seconds. So this seems to me like a good time for us to have tea, yes? Yeah. So let's take, how long for tea?
15 minutes.
15 minutes or so. At, according to that clock, 3:12 we'll be back again, okay? Seven wedges were the number, and each wedge represents 1 billion tons per year over 50 years. By the way, just a question for the audience here. How many wedges has the United States implemented since the year 2006? I'll take a number from somebody in the room. Please?
34.
How many?
4. 3, 4.
Identically 0. So, 7 wedges to mitigate, and now it turns out that the wedge notion has been reanalyzed. It's continuing to be reanalyzed because when there's no public policy, there's certainly research on what we could do. So an additional 2 wedges are needed because our emissions are rising. And now they're talking about a total of 21 wedges needed because the economy is in fact already decarbonizing. And then a more recent paper just published in 2013 says that 31 wedges are needed to phase out all emissions by 2060. So what's a wedge? Okay. So in 2006, the authors made very specific proposals for what a wedge represents. They are a little bit out of date now, but they are nevertheless very instructive for us to think about. So for example, cut electricity use in homes, offices, and stores by 25%. So that's a fully realizable goal. So for example, if the escalator is shut off when there's nobody on the escalator, something the Germans have done, something the Americans have never done yet, just simple ideas like that are one sort of wedge. How about stop all deforestation is another wedge in this sort of agricultural and forestry. I'm sure you're all aware that deforestation is a huge problem worldwide. Here's increased wind power to make hydrogen for cars. Now, at the time in 2006 when the authors wrote this paper, there was this notion that we were going to have a hydrogen economy. Hopefully some of you have all heard this notion. It was very popular in that time, that all our vehicles would be driven with hydrogen. There's still a community of people that believe that. You can buy it for $100,000, no, $200,000, a Toyota that runs on hydrogen or fuel cell. But the notion is that still could work. But I want to call your attention to this set of rings over here, carbon capture and storage. Install carbon capture and storage at coal to syngas plants. Install at 800 coal-fired power plants around the world. So the notion, even in 2006, was that at least 3 of these wedges would be associated with taking carbon dioxide out of the exhaust stream of a power plant, sequestering it safely and renewably underground, and that would represent an opportunity. So if we go back to these drivers and look at the energy wedges that are aimed to lower these lines, which are the production of CO2 from electricity, and we look at their effect on consumption, and we already need more wedges because the economy is decarbonizing, and so the question is, do we really need all the objects? So in many parts of the world, not so much the United States, but in many parts of the world, the issue of climate change and consumption are now combined with spiritual discussion. So you probably have read one of the most famous people in Europe is the Pope Francis, and he's recently written a book called Excessive Consumption a Sin, which in the Catholic Church world is a bad thing. That's a very strong statement. And so there's quite a bit of discussion about relating excessive consumption to the spiritual values that are associated with some cultures. Again, if we look at the role carbon capture could play, this according to the International Energy Agency in 2012, here's emissions of CO2, gigatons of carbon going into the future, and we see the role that energy efficiency could play, the role renewables could play, including nuclear, but you see that carbon capture and sequestration represents a reasonable range in this role of mitigating the CO2 into the atmosphere. And this is represents, by the way, a temperature rise up here at 50 of about 6 degrees C. Or down here it would be about 2 degrees C. In a few, either later this hour or tomorrow afternoon, we'll look at what the consequences to the world are for a 2 degrees C or 6 degrees C temperature rise. And we'll look at a globe of the Earth and see what the Earth looks like in that. It's something to look forward to. So CCS is 14%. So many of my colleagues in the chemical sciences in particular see an opportunity. Rather than put CO2 into the atmosphere, why don't we take carbon dioxide and do something useful with it? So-called carbon dioxide utilization. A very popular scheme. We'll come back and revisit it shortly. So why don't we capture it and use it for commercial products? So for example, if you look in the United States, there is CO2 used for various things, sodium carbonate, urea production, calcium carbonate, of course oil and gas is enhanced oil recovery. So we do have a market for CO2. Why not build on these markets and create new products? So rather than get our plastic bottles, the water bottles we're drinking out of, rather than make that plastic from oil, let's make it from CO2 that we get from the atmosphere. So the total use of CO2 in the United States represents about 100 megatons. That's the equivalent CO2 emission from 3 to 4 coal-fired power plants. Enhanced oil recovery is another 65. And total emissions from for the United States is 6,000. So you recognize that these two numbers alone are dwarfed by the actual emissions, which is to say we need to make a lot of products from CO2 in order to utilize it. And so we currently use less than 2%. Here's a nice graphic that I think illustrates even more. The data are a little old, but nevertheless instructive. So in 2009, 31,000 million tons, 31 gigatons of CO2 was emitted by all the coal plants in the world, just coal, in 2009. Well, let's go to the indices for chemical products and ask, what is the top 50 chemicals produced in the world? So that includes things like sulfuric acid and
Those of you who are students of chemistry will recognize many of these compounds. But let's just add up all 50 of them and come to the number. And that turns out to be 2,400 million tons per year. So you see all the chemicals produced, the top 50 chemicals produced by humankind in that year is a very small number compared to the CO2 emitted. Which is to say, utilizing the CO2 emitted from a coal-fired power plant to make new products is a nonsensical notion. It's not to say there might not be opportunities, particularly an opportunity to displace an industry that's using oil and emitting CO2 now with some sort of utilization scheme. But as a general scheme to deal with this is not practical. So now let's ask the following question. Let's suppose we do capture the CO2 from the coal-fired power plant. Maybe it comes to your mind, how much space do we need to store this? Because these volumes are enormous. So let's do a quick calculation. Here's the amount of CO2 emitted from a typical 500 megawatt power plant. I'm going to store it in a disk that's 10 meters thick, that's supercritical CO2. And let's say, for example, that the Earth actually occupies 80%, and so we can only access 20% of that disk, so sand, imagine packed sand. And there's the density and a plant lifetime. And so what I've shown here is a map. Hopefully it's not as clear as I'd hoped, but it's a map of Punjab. And here's Amritsar here, this sort of jagged. And this square here represents just the CO2 from one 500 megawatt coal-fired power plant. And this greater disk here represents what would be needed if we didn't separate the CO2 from the exhaust gas and use all the gases from the combustion process. So you can see this argument alone tells us that if we're going to store CO2 from a coal-fired power plant, we do have to separate the CO2 from the other gases. Otherwise, the aerial and volume requirements grow unreasonably. This is 5 kilometers. This is about 25 kilometers in radius. Yeah.
So what percentage do you take for this, like CO2 in the tanker?
12%.
That's a good.
That's right. Good question. So let's take a look now at, rather than look at wedges, let's look at the sort of circle of attributes that are going on. We have climate change going on. We have impacts. We all have a desire for an improved well-being, and we consume goods and services. We consume energy. We introduce CO2 that goes into the atmosphere, and then that changes the climate. So this is the cycle that we're sort of stuck in right now. And if you look at these blue words here, they represent opportunities for us to insert ourselves into the circle to try and mitigate the climate change associated with CO2 in the atmosphere, including conservation, efficiency, low energy emissions, and then carbon capture, and then of course this notion of geoengineering, which we'll come to later on in the course. So CO2 removal is really where I want to be for the remainder of this time. So again, we're back to where we were. I just wanted to point out these, we're not going to run out of fossil fuels. It's huge. And carbon capture and sequestration is really necessary to reduce emissions from the existing infrastructure. So in the hour and a half we've had together so far, a little less than that, what I've tried to do is lay out for you the scale of energy consumption and CO2 production. I've tried to make it clear to you that ending that production of CO2 instantaneously and switching to renewables is not feasible, it's not economically possible, and therefore we're left with strategies that mitigate the CO2 in the atmosphere, one of which is carbon capture and sequestration. So when you have a discussion with your colleagues about how to view this issue, there are 4 worldviews, according to our colleagues in Princeton who talked about the wedges. And the question you would ask yourself and your friends, first of all, are fossil fuels hard to displace? The answer is yes or no. And is climate change an urgent matter? So I would argue that fossil fuels are hard to displace, and I would say it's an urgent matter, so I would be over here. So these 4 views means that I really need to encourage current carbon capture. It needs to be here, and to make 3 degrees C, let alone 2 or 1.5, is a tough job. And if they're not hard to displace and it's not an urgent matter, then whatever you decide to do, like nuclear power or renewables, they're really not motivated by climate change. And I should probably tell you that there is a community of people, certainly in the United States, maybe in India as well, who are not motivated by climate change at all. They look at energy consumption and production as a business opportunity, and they see renewables and nuclear power as a business opportunity to make money. So they're in this space right here. And so you may find yourself in one of these areas over here. So our goal for the next few minutes together is to look at CO2 and ask, is it a greenhouse gas and how does it affect temperature? We'll find that there's overwhelming evidence that it is so. Are we responsible? And what do models say about the predictions in the future? So I'll start this now and we'll finish this at 2 o'clock tomorrow. So what do we know about the atmosphere and how is it changing? So I call your attention to this lovely island in the Pacific Ocean, the island of Hawaii. On top of the Mauna Loa Observatory is a station there where we measure CO2 in the atmosphere. It's called a Keeling curve, or I'll say a Y for a minute. This represents parts per million of CO2 in the atmosphere, and this represents the year. These measurements began in the mid-1950s and have been ongoing ever since. I'll come back and tell you what the squiggles mean, the wiggles. Okay? Let's just take the average for a moment. It's clearly going up. Our atmosphere is changing. Measurements are made all over the world, and they're honored by this man, Charles Keeling, and he's associated with this Keeling curve. He's recently deceased. So all throughout the world now, there are stations reporting the concentration of CO2 in the atmosphere. The one in Hawaii has been sort of the benchmark because it's been in existence for so long. It's also well above the, it's very high up on the top of this mountain, and so most of the weather that passes goes underneath it, so it's a very stable platform. There are measurements in the southern hemisphere and the northern hemisphere throughout the world. In January, this was 402 parts per million, and as you probably know, everywhere in the world now it's above 400 parts per million, which represents a significant increase. So here's the world's global temperature. Here's a function of the concentration. Here's a year, and we recognize right away that there seems to be a correlation between the amount of CO2 in the atmosphere, as shown here, and the global mean temperature as shown by these bars. So is this a correlation or causation? This is a critical component of our discussion about climate change. Because if they're not causal, then our concern about CO2 is misplaced. So that's something we really need to address. So the hypothesis is that increased CO2 leads to global warming. So the question is, are they increasing? The answer is yes. Those measurements are very clear. And the question is, what's the mechanism by which that would change the climate? And in fact, can we measure it? So we're going to try to address this question now, and we'll come to this question in a few minutes. So who was it who first started talking about CO2 in the atmosphere? Students of chemistry will recognize this man's name, Arrhenius. He's forever associated with how chemical kinetics occur. But interestingly enough, at that time, which is in just about the turn of the 20th century, he published a paper in which he said if we doubled the amount of carbon dioxide in the atmosphere, he expected the temperature of the world to go up by 5 degrees C. He made a refinement to that calculation and came up with the number 2.1 degrees C. It's really quite amazing. We're going to come back and look at a graph in a few minutes that shows what is the effective doubling of CO2 with our best possible models. And the answer is it turns out to be about the same number, although the reasons are very, very different. So how do we imagine what CO2 does in the atmosphere? And the way we have to start is we have to do an energy balance on the Earth. And these are calculations that are straightforward in concept and tedious to do properly. But we want to calculate what is the temperature of the world with and without CO2 in the atmosphere, or with and without an atmosphere forever. So we have sun, which is radiating. It's a black body at a few thousand degrees Kelvin. And we have the Earth, which itself is radiating as a black body at a few hundred degrees Kelvin. So we need to do an energy balance in this process to predict what the average temperature of the Earth. Because, of course, we are at equilibrium. That is to say, there's no transience in the temperature, at least on sort of geophysical timescales. So black body radiation is what is associated with this.
And we know the physics behind black body radiation, the flux of energy, energy per area per time is a constant times the temperature of the power. So now we have the energy from the sun impinges upon the Earth, and the Earth receives a fraction of it in proportion, in radial proportion. And so that's why we have the radii there. And let's see, the energy out from the Earth represents the Earth radiating with its area and its T to the 4. So we have two different temperatures, the sun and the Earth. And we just equalize these two. That is, the energy coming in from the sun equals the energy out from the Earth. That's conservation of energy. And you can do the calculation. It takes a few steps and you get a number. You get some data, and the number is 6 degrees C. So that's just assuming that the Earth is a ball and the sun is a black body. And that number is off by about 10 degrees C. So we ignored a few things, so let's go back and consider them. So we ignored the fact that clouds reflect the sun differently than land and differently than sand, the so-called albedo coefficient. That's really how much light is reflected when sunlight impinges on it. It varies a lot, and so we need to take that into account. And we recognize that about 30% of the sun's energy turns out to be reflected. And so we can take that into calculation, and we redo the energy balance. Let's do that calculation again, and now we have the albedo factored in there, and we get minus 18 degrees C. So this simple energy balance alone tells us that we're close, but not quite from what the actual temperature is. And of course, the difference between this temperature and this temperature is the role of the atmosphere and the so-called greenhouse effect, which is what stabilizes our planet. So let's take a look at some more detail at what a physicist has to do in order to calculate what the temperature, the black body temperature of the Earth is going to be. So we have incoming solar radiation. In the units, it doesn't really matter, of watts per square meter. And then some of that is reflected, some of that is absorbed by the atmosphere, some of it makes it to the Earth. The Earth itself is a black body, and it's radiating up this much energy, some of which goes outside, but some of which is reflected back from the gases that represent the atmosphere. So these would absorb emitted radiation and radiate it back and change the temperature of the Earth. And so if we just look at these numbers, they represent the conservation of energy. There's 340 in, reflected 100, 240 coming out, so that's good. But this approximate sign is critical because we recognize that small differences in these numbers represent what's called the radiative forcing. And a way to think about this is to say that changes in the radiation up and reflected back force the black body temperature of the Earth to change. So if we introduce greenhouse gases and more of this energy is reflected back, then the black body temperature of the Earth has to go up so that the total emitted energy remains the same. And so this represents the short picture of what the greenhouse effect looks like, and it tells us why it is our planet has been so stable. The number one greenhouse gas turns out to be water. We'll go back and talk about that in a few minutes. So let's look now at what would be interesting to measure. So let's take some satellites, and we'll put them to measure the incoming radiation, the reflected, and the outgoing radiation of the Earth. We'll use satellites, which are mainly infrared cameras. And ground instruments we'll use to measure how much light lands here on the planet at a particular place, and of course how much is radiated up. The difference between all these numbers is the radiative forcing. So this is now a measured number. Right? So now what are we going to do? We're going to compare this measured number to the changes in the greenhouse gases that occur on the planet Earth over a decade. And compare them and see what's up. Amazingly enough, this was just published in 2015. The first, I would say, sort of definitive, concrete, quantitative measurement of the greenhouse effect of CO2 on the planet. Here's the radiative forcing that I just mentioned, calculated from those instruments. Here's the amount of CO2 in the atmosphere, and you see the radiative forcing not only follows this oscillatory trend, which we'll come back and figure out in a minute, but it gets the average trend in temperature correct. So CO2 is a greenhouse gas.
It's changing the temperature of the planet in exactly and quantitatively the ways physics says it should. No models needed, only data. So, it's our CO2 is warming the planet, and it's doing it by radiative forcing. And the role of humans in this is sort of established. Sorry, Bernard, was that you? Okay, so let's ask ourselves, what is the composition of the Earth's atmosphere, and what role does this affect? So these are the volumes in ppm, these are the volume percents, and you recognize that carbon dioxide is only 400 parts per million, but it represents this sort of key player. It's difficult for some students to come to terms with the fact that such a small number, 400 ppm, has such a dramatic effect. But it does, it's been measured, and the interesting thing that we should ask, and we'll come look at a few slides later on, what are the consequences for even these small changes in CO2 in the atmosphere? So this radiative forcing, remember, changes in the greenhouse gases change the radiation reflected back to the planet and force the black body temperature to a higher number. Or a lower number, as you see what happens with aerosols. Aerosols in the atmosphere actually reflect more sunlight and change the albedo, and they are a negative radiative forcing. Here's CO2 and methane, other greenhouse gases, and what you see is the total net human activities exhibit strong radiative forcing towards in a positive sense, which is to say we've increased greenhouse gases. Measurement of these quantities in both time and space is a significant challenge for those of you that are scientists. It represents an extraordinary opportunity to be both intellectually engaged as well as working on behalf of the planet. So CO2 in the atmosphere absorbs the outgoing radiation, causes the forcing, and the Earth must heat up to counter this forcing and maintain. So which one is worse? So these are all attributes of what makes a greenhouse gas worse, and in particular what its lifetime is. So this is an interesting thing about methane, because many of you have heard that methane is a significant problem in terms of climate change. It is a significant problem. This is particularly true in the United States and other parts of the world where natural gas is being used to replace coal for energy production. So natural gas is fracked. Hydraulic fracturing is a mechanism to produce a lot more natural gas. And as a result, a lot of methane is seeping into the atmosphere. Methane also has several natural sources. So, for example, the flatulence from cattle. And as the Western world in particular develops an appetite for meat, you want more cattle. The cattle fart and introduce a lot of methane. It turns out it comes from cattle flatulence. But interesting, the lifetime of methane is only about 10 years in the atmosphere. Can anybody guess? It's presumptuous of me, but I'll just ask. What's the final product when methane decomposes in the atmosphere? What does it decompose to? Anybody know? Yeah. So the end result is that methane is not only a strong greenhouse gas itself, its short lifetime is hardly anything to be happy about because it just decomposes into carbon dioxide. Water is in fact the worst greenhouse gas. It has a very strong, so why aren't we worried about water in the atmosphere? And in fact, why don't you just say, well, Professor Reimer, rather than worry about CO2, why don't we just take some water out of the atmosphere? Well, it turns out we don't really control the amount of water in the atmosphere. Mankind has very little effect on that. And it turns out the amount of water in the atmosphere has not changed much in at least 3.5 billion years, as evidenced by analysis of geological samples. It also turns out water is a positive feedback on whatever does happen. So as the planet gets warmer, more water evaporates and we have a larger greenhouse effect. And of course it gets colder, the opposite is true. So what happens with carbon dioxide is that or methane, as we increase it in the atmosphere and the greenhouse effect increases, actually water is an accelerator of the greenhouse effect. So we are worried about water, but we're worried about the consequences of it because of the result of CO2. So, are CO2 levels increasing? Yes. By what's the mechanism? Well, it's radiative forcing. And can it be measured? And the answer is yes. So let's talk about some of the consequences then of what happens when we have a greenhouse gas effect and the black body temperature of the planet is increasing. So the question then becomes, well, what's the weather like in Amritsar, and is there any connection between today's foggy day and climate change? And that is a vexing problem because, according to this famous humorist, climate is what we expect and weather is what we get. In fact, climate, that word climate means a statistical analysis of the long-term averages of things that you experience daily. So weather is today's events, and we talk about the probability of it being foggy, and climate is the long-term measure. So if we look at land and ocean temperatures and how they compare with the average since 1880, and this was data taken from July 2015, the National Oceanographic Association of the USA has a very nice website, NOAA.gov. You should check it out sometime when you're bored. They have all these really wonderful graphs. And here you see record warmth in various parts of the world. Some places, to be sure, that are cooler than average, but I think your eyeball can easily detect that the planet is warming, and as evidenced by the pink colors. If you look at the United States and ask what about weather events for 2015, there are an extraordinary number of weather events that are unusual and anomalous. And you might ask yourself, is there a connection between climate change and these? And of course, that's where we want to go. Let's look at the top 10 warmest years. And you recognize that since 1998, the 10 of the hottest years are all given recently. And we are on track. We will know soon, but it is believed that 2016 will be, in fact, the warmest year ever on record. So the global average combined temperatures are definitely increasing. And here are some news clips that just reinforce that notion. So one way to graph that is to look at the data that comes from a whole variety of sources. This is time from the year 1000 to more or less the present day. And here's the northern hemisphere temperatures for which there are the most data. The gray here represents all the different kinds of individual measurements, and the blue and the black represent reconstructions with different degrees of smoothing. And you can see that something interesting is happening recently, and this recent trend is quite unusual. This is, for me, the most powerful visual graphic, so please watch it for a moment. It represents temperature as a function of time. And it's as you go from around the clock, the calendar, from December around. So I'm going to run that one again for you, so you get the full impact. So again, these are the temperatures recorded at different times of year on the radial clock. You see there was a couple of cold years there at the beginning of the 20th century. So to me, this is a very effective way to show that the planet is warming. So temperature is rising because of CO2. The CO2 is from our energy production, and the greenhouse effect is established. Our role is established. Temperature is rising. An important thing in climate science is the if-then connection. If this is true, then this must also be true. And it's an important way to validate and to deal with criticisms, many of which are quite legitimate. So, for example, if the Indian Ocean is cooling and the planet is warming, how can that possibly be so? And so scientists need to go and look at these sort of if-thens. So things that ought to matter, for example, would be sea levels and heat content of the oceans, glaciers, Arctic ice masses, and extreme weathers, because all of these should be affected if the average temperature is rising. So perhaps you don't believe these temperature measurements. Let me show you some other proxies for temperature. So, for example, scientists have been looking at these for a long time, at least 30 or 40 years, to try and cite some things out. So one of them is the probability to have extreme weather. So you think about the average temperature in Amritsar as a bell curve, a Gaussian distribution, and if the average temperature changes a little, then the extremes change a lot. And so this was brought to light in this absolutely beautiful paper. It's a little old now, 2012, Jim Hansen was one of the leading scientists at NASA. He's now retired, but he published this really fascinating paper, which I believe, and when I speak about climate to the public, is one of the most powerful visual demonstrations of the role of temperature. So let's take, for example, the average temperature, for example, in San Francisco from this period of time. And I record those numbers as a function, and then I make a plot of them, and I obtain a bell curve. And we all know what those look like. There are error bars. So, for example, the average in San Francisco turns out to be 12C. And by average, I mean day-night over the whole year. Okay? And then these represent the distributions. And you recognize that 2 and 3 sigma events are very rare. Okay? That's what it means to be in a bell curve. So what these guys did is they said, how much of the Earth has experienced a temperature larger than 2 to 3 sigma in recent times? So we're going to make a map of the world, and the colors on the map of the world are going to represent the 2 and 3 sigma events as a function of time. And what's the comparison data? They'll take the data from those parts of the world, from this window of time, and make an average of them. Okay, you with me so far? So, as I mentioned before, a very small change in the average has a very large effect on the tails. So here, for example, is the difference between these two curves, which shows a very large peak here. So here's their plot. These are extreme weather events. So red is 2 sigma and brown is 3 sigma hot. Purple and dark blue are 3 and 2 sigma cold. So here's the world in 1955. And remember, the average for this is 55 to 81. Here's the world in 1965. Here's the world in 1975. Here's the world in 2011. And as we said before, 2015 and now 2016 are even warmer still. So the probability to have an extreme warm event is much, much higher because the average temperature has moved up slightly. A very, I think, powerful graphic. Now, what are the consequences of warmer weather? There are many, and I'll come back to them in a few minutes, but I want to close today. What time do you, how much time do I have?
Oh, you have 5 minutes.
Okay, just enough time. So, 2 men are walking on the streets of Italy in the summertime, and they're talking to each other, and they say, one of them says to the other, let's go to a bar and have a cup of beer, because if we stay out on the streets, we're going to get into a fight with the other gang. Well, they do get into a fight with the other gang, and as it turns out, Romeo tries to intervene between the 2 gangs. 2 deaths happen in that brief period of time, and so begins one of the most famous tragedies, Shakespearean tragedies, in all of English literature. And it really starts with this claim that one man makes to the other, it's a hot day, and if we go outside and run into this gang, we're going to start a brawl, start a fight. Is that true? If it's warmer than the average, are we likely to get into a fight? And so in the era of big data, my colleague Solomon Shing at UC Berkeley and a couple of his now former students asked the following question. What is the relationship between temperature and violence? Now, we have to be careful here. We're not talking about absolute temperature. It's not like the warm places of India are more violent than the cool places. The question is, what is the temperature relative to the average? And so Solomon and his colleagues have constructed, first of all, this nice map in which we look at the southern hemisphere, sub-Saharan Africa, Eastern Africa, sub-Saharan Africa, and the whole southern hemisphere. Here's the percent increase of conflict as a function of the temperature for East Africa. Now, I want you to call your attention that the error bars are pretty large. And they have to be large because these kind of events in temperature are rare. It isn't very often that it's minus 2 degrees C colder in Eastern Africa. But nevertheless, the trend seems to be quite clear. Now, look at the difference here. If you go up by 2 degrees C, you're talking about an 80% increase in violence. How about civil war in sub-Saharan Africa? That's the blue region right here. Notice it's a different temperature scale, but you still see a significant increase in the probability of violence with increasing temperature. How about in the entire global tropics? Same relationship. increased violence and increased temperature. Now there is a tendency, and I apologize, that some Americans would look at data like this and say, well, that's true for those people, but it's of course not true for us. But big data is phenomenally frustrating to many of us. So here's violent personal crime in the United States. Here's the jurisdiction, the temperature, degree C, and here's the change in probability. Here's rape in the United States, same relationship. And here's intergroup violent retaliation in the United States, same relationship. So two communities are taking climate change very seriously in the U.S. One is the police, and the other is the armed forces, because they see these kind of increases as being clearly related.
But it is opposite in India.
It is what?
It is opposite situation in India.
Political.
Kashmir is very cold.
That's a good joke to end today on. We're going to come back tomorrow at 2 o'clock, and I'll revisit some of the other consequences of CO2 emissions, and we'll go on from there. Okay? So we're all set? Thank you. I'll see you all then.
Pass on the slides.